So for my final project in MSE3210, I decided to deal with a 7050, a high strength, high corrosion resistance aluminum alloy. You see right there, it's about a 12.5 millimeter cube. And what I'm doing right now is I'm just getting the mass of it. After that, then I'm going to put it into a furnace that's at 135 Celsius and measure the time for it to hit 120. The initial temperature I measured before, it's about 17.5 Celsius. That's true for both before and after solutionizing, which is what I'm going to be solutionizing my material after I get the initial heat capacity of it. And in a couple seconds here, you'll be seeing a furnace that has 1 adiabatic surface, which is important for my area calculation, surface area. And yeah, that's the project I have. I'll go through some live videos in a couple seconds.
So it ended up taking me about 7 minutes and 32 seconds for that sample to warm up to 120 Celsius from 17.5. And now what I'm going to do is start solutionizing my material, which is getting it to a high enough temperature so that some secondary phases will dissolve into the aluminum matrix. And I'm going to be doing that at 477 Celsius for 90 minutes, which is the traditional solutionizing standard for a 7050. And after that, I'm going to go back through the same test I showed you before. I'm going to set this furnace to 135 Celsius overnight after I finish solutionizing here, just to make sure that the temperature is going to be uniform throughout it. And from there, we'll see what differences there are in the heat capacity. You can't tell with the quality of a camera I have, but it looks a little bit different. Looks like it's going to be about 135.7 Celsius.
So as for my calculations, first of all, I just wanted to show you that lump capacitance is definitely valid here, because you know what H times L C over K. The H value, it pretty much doesn't matter whatever H value you use, lump capacitance will be valid considering just how high thermal conductivity it is. Alright, so for the known conditions, there's two time-dependent conditions. Our initial temperature is T sub I at time equals 0, and at some sort of final temperature, we know T sub F, which is 120 Celsius for my calculations. And just plugging in the energy balance equation with lump capacitance, I'm assuming radiation is negligible here, so we just have the energy either going in or going out, depending on how you look at that, heading into energy stored thermally. And from this, I'm just trying to solve for C, right? And the important thing here is just seeing that time equals 0, T sub S equals T sub I, so the initial temperature, and so therefore you solve for your C1 through that. And yeah, from this, just manipulating the equation to get it into something to solve for C, the specific heat of my material. And yeah, just plugging your TF and temperature final into this equation, where this T sub S should actually be just T sub F. And from here, it's plugging in the different constants that I have. And for the convection heat transfer coefficient, I looked through the textbook. It seemed like the best value to use was H equals about 15 watts per meter squared. As I'll get through in a little bit, that's probably not right, but that's the value that seemed like the textbook was using for the type of setup that I have with the furnace and not forced convection. And yeah, from here, another important thing, rho times V is just going to be M, which is 5.74 over 1,000 kilograms. And yeah, these are the two times that I got, 452, so 7.5 minutes, which is about 6.5 minutes. And as a result, just plugging in this equation here, we got 449.9357 joules per kilogram degrees Celsius before solutionizing, and a significantly lower value after solutionizing. And these numbers aren't numbers I agree with. They're about half of what I would expect for aluminum alloy 7050. Generally, the range is somewhere between 800 and 1,000 joules per kilogram degrees Celsius. So something's probably off, and again, it's probably just the convection heat transfer coefficient. But anyways, the sources of error here that I notice at least are keeping the furnace door open too long. Obviously, if you keep the furnace door open too long, the temperature isn't actually going to be uniform at 135 Celsius everywhere. And how the furnace responds to a change in temperature. So at least for this furnace, it will sometimes go above 135 Celsius if you have the door open and temperature initially goes below, because it's trying to get back to 135 as quick as possible, uniform throughout. And so depending on how it responds to that, it could actually quicken your sample heating up more than what we're trying to do by comparisons. And yeah, I already mentioned this, definitely a wrong H value. So yeah, that's it for my work.